Thank you all for being here today. So I'm not a real doctor like Dr. Rosas. I'm a plant doctor, but plant disease is important too. So I'm here to talk about our cool technology that's helping to shed light on plant diseases. So when you hear the phrase plant disease, maybe some of you guys think about the Irish potato famine. We know that this famine was caused in part by a plant disease called late blight. And now you may think of this as a historical problem, but it's actually still a massive problem in modern agriculture. This background picture here is a hot spot in a potato field that I worked in the summer of 2018. This grower went to sleep on a Friday night thinking he had a lovely crop, had a wonderful weekend, and woke up on Monday morning to thousands of dollars worth of losses due to this single hot spot. And 2/3 of this 80-acre potato field had to be completely destroyed. There was no saving it. So this highlights the importance of early disease detection. If he knew on Friday that the weather over the weekend was really going to set this disease off, what more could he have done to stop it before it completely damaged his crop? If we had an early disease detection system, we could potentially save millions of dollars, but also help reduce food insecurity caused by plant disease. So now we're going to zoom back out for a second and go use an analogy to human health, Dr. Rosas. So think about the last time you had the flu, and you probably felt awful. I know that I did. But days before I felt terrible, I was already infected with the flu. And the same is true for plants. Before they show any signs or symptoms of being sick, they are already infected. And when you had the flu, maybe there were some subtle changes that were occurring in your body chemistry that could have indicated you had the flu, but that you weren't able to notice. Maybe your white blood cell count was different. So we know that both plants and people will show these very subtle changes in their physiology and chemistry before they actually show any visible signs of being sick. And we've been able to harness this phenomenon by combining 3 seemingly disparate disciplines: plant pathology, technology, and remote sensing, as well as data science by using new machine learning applications. And when we combine these together, there's actually already a discipline forming there, and it's called precision agriculture. And I'm sure many of you guys have heard this phrase before. But to me, precision agriculture is really a philosophy. It's a way of thinking about and managing a farm. And in order to realize this vision, this philosophy of precision agriculture in plant pathology, we really need those disease detection and monitoring methods that are fast and accurate. To do this, we take advantage of the fact that light interacts with plants differently when they're sick. So light will come in, bounce off of plants, and then depending on plant health, it will change the way that light is bouncing off. So if we can measure how that light is changing, then we can more precisely understand plant health. So the light will change when plants are drought stressed, when they have nutrient stress, when they have disease. And we can see all of these things with our eyes, but the light will change long before we could see these things with our eyes, maybe in more subtle ways than we could notice, or maybe in the types of light that our eyes can't actually see. So we've harnessed this together and combined it into a spectrum-based algorithm that we were able to use to do pre-symptomatic disease detection with really high accuracy. And we discovered that when we account for underlying pathogen biology and those subtle changes in disease physiology, we were able to do this much more accurately. And then this is where the WRF AP project came in. They helped us design a study so that we could test whether or not this would work in the field. We worked with some wonderful colleagues at Michigan State University, as well as some phenomenal junior scientists to see if we could use this from an aircraft. We also worked with industry collaborators, a wonderful crop consultant, so that we could really see if this technology would work. And we were really excited because we found that we could use light to measure how these plants are changing when they're sick and to map specific disease incidents. So when a plant is infected, any one part of it, the rest of the plant will know. It might not be able to do anything about it, but it will know that it's infected. So we can take advantage of that change in plant chemistry to map diseases. So over here on the left, this is what a field might look like to your eye. That's my husband's eye up there. Over on the right, this is what this field looks like to our technology. And take a look in that upper right-hand corner. It looks totally fine to us, but we can actually see that the foliage of the plants is reflecting the fact that there is really low disease there. And we could maybe use this one day to help us know when we have low incidence of disease before things get really bad and we're faced with major financial losses. So to summarize, our preliminary results suggest that aerial detection at these really low levels is possible and that our technology will likely work in real-life applications. And we actually found that the aerially acquired data was actually giving us a better insight into crop health than just looking at the canopy alone. The further investigation is ongoing to see how we can translate this to more accurate pre-symptomatic detection. And once again, I'd like to thank the WARF AP project for helping us do this. So our team is comprised of 3 individuals, my 2 PhD advisors, Dr. Amanda Gevins, who's a global expert on potato and vegetable pathology, and my co-advisor, Dr. Phil Townsend, who's an expert on remote sensing, and me here at the middle, trained by the 2 of them at these 3 different disciplines. So our work has resulted in 1 patent, over about $500,000 worth of funding, 4 publications, and also 1 brand new R1 laboratory. So if you'll forgive a young scientist for ending with an advertisement, the Gold Lab, run by myself at Cornell University, is now recruiting. My brilliant advisors are going to be advancing this work specifically for our Wisconsin potato growers, but I'm looking to expand this to other specialty crops, particularly grapes and perennial crops. So our specialty crops are the foods that you like to eat, foods you like to drink, coffee, wine, beer. Those are specialty crops. Peaches, pears, apples, almonds. And these crops are so often forgotten when we think about plant tech innovation. And if we don't protect them and invest in those technology, we will not have them moving forward. So I'm looking for students and researchers to join my program to expand this work. I'm looking for funding to help support those students and researchers, as well as grower and industry collaborators that can help us advance this towards the field more quickly. Once again, my name is Katie Gold, and I'll be around for the rest of the day, as will my advisor, Dr. Amanda Gevins, and we'd love to chat with you all. So thank you.
Thank you, Katie. And yes, congratulations on your appointment as Assistant Professor of Grape Disease Ecology and Epidemiology at Cornell. So from vodka to wine.
Yeah, right? French
Awesome.
fries to wine, not so bad.
Do we have any questions on this research?
Yeah, so in this case, you're dealing with a fungal disease. So how about the bacterial and viral diseases? Do you find the same thing?
That's a great question. My honest answer to that question is that we don't know yet. This is really early stage, but everything that we've seen on the ground and in our controlled studies suggests that yes, this technology is absolutely applicable to different diseases other than fungi, bacteria, viruses, but the real exciting research moving forward will be how do we move forward in the field with detection of those changes, and how do we make sure that when our detections are truly robust, and we're detecting a bacterial disease and that specific disease, and we're not conflating it with anything else. But everything that we've seen on the ground suggests that it would be absolutely applicable. Yeah.
How do you see this being used commercially? A farmer would pay to have somebody fly over their field once a week, or
Yeah.
what are your thoughts?
That's probably what I would see as well. I'd likely see it as a service agreement. I don't think it's really worth an individual grower's time to learn how to do this by themselves when there's a ripe opportunity, and there's already an industry in place with our crop consulting companies. And here in Wisconsin, potato growers rely pretty heavily on aircraft-based sprays. So I would see that as the most likely path to commercialization. All right. Oh, yeah.
So if you do detect it early, then what's the next step? Is there a available treatment to stop it?
Yeah, so in the case of potato late blight, we have fungicides that we could use that could not retroactively, that have what we call kickback action, so they can stop an established infection. But what it would also allow us to do is if we were able to find disease when it's maybe at that only one plant level, we could better protect the rest of our crops. And therefore, if we knew we had a reliable way of detecting when it's at that really early stage, we could avoid spraying otherwise. But so you could use a fungicide, or if you don't want to do that, you could also rogue that plant. So with an annual crop like potato, you could remove that potato. Thank you all.